Hello everyone. For our Fall 2020 Fluids project, we designed a water clock so that we could tell time after the machines take over. Water clocks were invented in Egypt during the 16th century BC. Initially, they were used to help with agricultural production. These early water clocks had a constant flow of water into the tank, like shown in the picture. Evangelista Torricelli didn't want to rely on this constant flow, so he designed a container that would provide constant flow. Again, we built this water clock so that once the machines refuse to tell us the time, we can still get an accurate time.
In class, we learned about Bernoulli's equation. Here, the equation has been manipulated to determine the velocity at the bottom of the container if the pressure were constant. In reality, we'd have to take into account the changing of the height of the water level, as well as the changing pressure. When the water level is h, the surface area of the water is A equals pi r squared. This means that the rate of change of the water volume is shown in the slide below.
From here, Torricelli's law can be manipulated to solve for the ratio of height to radius for a linearly draining tank. We then modeled the tank using this ratio and 3D printed a working model. This means that the water level will drop at a linear rate, which makes it possible to turn a clock dial. We took the model shown in the last slide and 3D printed a tank to produce linear flow. We then drained water from one container to another. We used a flotation device to translate the linear flow to the clock face. Our original plan was to have a 24-hour clock. However, this idea was dropped when we realized the tank would need to be approximately 5 feet tall. To get a full rotation of the clock, we created a gear with a circumference that is equal to the height traveled by the flotation device.
We faced a few design challenges along the way. Like we stated before, we could not hold enough water to create a 24-hour clock. We also struggled with getting the rack to rise completely vertically. It was also very difficult to create an exit nozzle that was the correct size to allow constant flow without a constant stream of water into the tank. We had to create a flotation device that had enough buoyancy to lift the rack with enough force to change the clock. Another design challenge we saw was that small water droplets would form through the PLA after a long period of time. Also, surface tension was a slight issue because with a small hole, the surface tension would be greater and the water would not flow.
This is our final design. Here we have redesigned a gear ratio for complete circumference of the circle. We also created a smoother rack movement using a 3D printed guide. We used our extra time to create another tank that drains in 10 minutes. We also reinforced the structure of the water clock with angle brackets at its base.
If we had more time, we would design even more tanks that drain at different time periods. We could also seal the 3D printed components so that the water does not leak through the PLA. We also discussed making the tanks out of other materials like wood or even injection molding. Another improvement we would make is the smoothness of the rising